In this video, I want to talk about a really important idea involving inverse trig functions, and those are the domain restrictions that are imposed when we work with inverse trig functions. And these are often overlooked, but they are incredibly important to pay attention to, and I want to hopefully help us to understand why they're here as opposed to just something we have to memorize. So first things first, inverse trig functions are incredibly useful because they allow us to work our trig functions backwards. Um, if you recall, we plug angles into our trig functions, whether it's sine, cosine, tangent, secant, whatever. Here I'm just picking on the sine function, but angles go into a trig function and ratios come out, right? Those are the outputs. For the case of the sine, it's specifically like the y over the r or the opposite over the hypotenuse, right? Depending on what definition of a trig function you're thinking about. So angles go into trig functions, ratios come out. Inverse trig functions work the other way around. We plug our ratios, like the opposite over hypotenuse, into the inverse trig function, and it tells us what angle would generate that particular ratio. Okay, so again, we could work this in reverse. There is a huge caveat here that if we don't pay attention to is going to bite us in the butt time and time again in this course. However, this angle right here that came out of the sine inverse function is restricted. It's only allowed to be between negative 90 degrees and 90 degrees. Or if you're thinking radians, then from negative pi over 2 to pi over 2. That's it. Okay, so let's take a look at why, and then let's kind of see where this might come, where we're going to encounter this. So why? The y is has to do with the fact that we want this to be an inverse function. And if you recall from algebra, inverse functions must be 1-to-1 in order to run the thing backwards and have the backwards direction still be a function. The best way, or one of the easiest ways to check for 1-to-oneness is to use a horizontal line test. Now, we haven't got to graphing the trig functions yet. That comes along later, but for a brief sketch, here is roughly the graph of sine. We won't go into all the details yet. And if you look at this graph of sine, you'd say, well, this thing is clearly not 1-to-1. It fails the horizontal line test. This horizontal line hits many places. In order to be 1-to-1, we need a horizontal line to pass through this thing and intersect the curve only one time. So a trick we pull in mathematics is we say, well, let's not look at the whole curve. Let's just look at part of it. What if we were to just focus on, let's say, from here to here? And we said, forget the rest. Let's delete it. Looking at that chunk of the sine wave is 1-to-1. If you slip a horizontal line through it, it intersects at only one point. So this chunk of the sine wave is 1-to-1. And if you noticed, I deleted it, but it covered all the possible outputs of sine. It went from the lowest point to the highest point. Now, where this occurs, these cutoff points, now this x-axis is in terms of angles, we'll see, but this is at 90 degrees, and this is at negative 90 degrees. Or again, if you're working in radians. So when you're plugging an angle into sine, the sine function, this guy in its entirety, will take any angle you want to plug in. Even if it's an angle way down here, plug it in, boom, there's your corresponding ratio. For the sine inverse function, however, it only knows this region. It only knows and understands this little piece. It's not a complete sine wave. So therefore, when you plug a ratio into the sine wave, or sorry, sine inverse function, it's going to spit out some angle that's only stuck between negative 90 and 90, or negative pi over 2 and pi over 2. So that's really important to remember, because let's again look at a general sine wave here. So just something that looks like that. What we'll find later, unless you already have explored it, sine is bound by these heights of -1 and 1. So let's just say that hypothetically we were interested in finding for what angle does sine equal a height of a half, right? So a height of a half would be like this line right there. Tried to cut it in half. Well, you could see that there's many angles for which sine equals a half. I mean, whatever this angle is right here, we obtain a height of a half. Whatever this angle is here, we obtain a height of a half, a half, a half. There's infinitely many points or infinitely many x values you could plug in here rather that would make sine give us 1/2. So I could find that angle. In this case, we could use our unit circle because that's a common ratio, but let's go ahead and use inverse trig instead. If I want to find this angle, I could invoke inverse trig. I could say, okay, well, that angle would have to equal sine inverse of that ratio. Okay. And we can plug that into the calculator if it's a ratio we don't know, or we can use our unit circle knowledge. But the thing to remember is because you have invoked this notation, this whole picture doesn't apply. The only thing that applies to this function is from the -pi/2 to pi/2. So the only answer that's going to come out of this guy is that one angle value right there, right? Which we know from our unit circle, this would have to mean that x is pi/6 or 30 degrees. Okay, it's not going to tell you about all these other ones because again, in the eyes of sine inverse, that's all there is. So it's important to know that because depending on the type of question you're answering, you might want all these other answers as well. Those might be legitimate answers for your problem. And so we can easily go find them. That's not going to be a problem, but you just have to know that they are there and that when you use sine inverse, it's not going to necessarily tell you about them. It is going to give us enough information to go find them later, but there's a little more work involved if you want them. So that's just something to keep in mind. We have restrictions for the cosine and tangent function as well. And the reasoning behind the restrictions is exactly what we drew here. If you were to graph the cosine function, there's a logical place where you would break it up so that you would get a one-to-one curve and therefore be able to talk about the inverse. It's different than this. Same goes for the tangent inverse function. If you were to graph tangent, there would be a logical place to chop off some of it so that you get a curve that a horizontal line can pass through only one time. So let's just write those out real quick. If cosine of some angle gives you some ratio, then that ratio can be found by taking cosine inverse of that particular angle. Oh, totally messed that up. Look what I did. It's not correct at all. I was going to say, what got me is like, wait a minute, we don't plug angles into cosine inverse. We're supposed to put ratios in there. Let's do that again. Let's see. We get an angle out from our cosine inverse after we have plugged in the ratio we're trying to obtain. And remember, that angle, because for this function, we've had to restrict the domain. So this angle only exists in the case of cosine inverse between 0 degrees and 180 degrees, or 0 and pi. If tangent of some angle gives me some particular ratio, right? Like an opposite over adjacent, then that angle can be found by taking tan inverse of that particular ratio. However, this angle is going to be restricted, right? Remember that there's infinitely many angles you could plug into the trig function to get a particular ratio. But when you're using inverse trig, there's only one angle that it's going to point to for that particular ratio. If you want the others, you got to dig deeper and go find them. So this angle is strictly less than 90 and greater than 0 degrees. or 0 and pi over 2. Similar to the sine case, but it's not allowed to equal 0 or 90. If you haven't seen yet, tangent is undefined at those values. So here's what I do to help me remember this, because I think these are kind of hard to remember. So I've made this my habit. If I'm doing a problem and I encounter sine inverse, as soon as I see that, I draw this picture. That's to help me remember that whatever I get out of here, whatever this becomes, it's going to be stuck between negative pi over 2, or negative 90 rather, to 90. Or if you're working in radians, negative pi over 2 to pi over 2. When I see cosine inverse, the second I see that, I draw this picture to remind me that cosine is, or inverse rather, is only going to give me an answer from 0 to 180 or 0 to pi. And then lastly, as soon as I encounter tangent inverse, I draw the same picture I do for the sine. 0 degree, I'm sorry, not 0, negative 90 degrees to 90. I just try to remember that it's technically not defined at those points. Okay, so those are what help me remember that these inverse functions have domain restrictions. And if you were to type into the calculator, hey, what's cosine inverse of, 0.85? It'll give you some answer in degrees or radians, whatever you want to work in. But remember, that is not the only angle answer that you could plug into cosine and get that out. There's infinitely many angles you could plug into cosine to get 0.85. The one that the calculator is going to tell you is going to be the only one living in that region. And if you want any other ones, you got to go find them.